Friday we talked about L'Hopital's rule, lesson 4.6. We got through examples 1 and 2 and talked a little bit about how we format them, how we should display our work and all of that. So let's look at example 3. The limit as x approaches negative infinity of x squared over e to the x. So I would start with a kind of mental plugging in. If I have negative infinity and then I square it on top, that's going to be positive infinity, right? On the bottom, e to the negative of negative infinity, well, that's essentially e to the positive infinity. And so at this point, we're kind of looking at a positive infinity over positive infinity, right? And that was one of our indeterminate forms. So I'm going to start off. What's important that we do when we're doing our free response, we need to individually state our limits here. That way we can say that we can use L'Hopital's. So the limit as x approaches negative infinity of x squared would equal positive infinity. And the limit as x approaches negative infinity of e to the negative x would equal positive infinity. And if you want, you can mention something about indeterminate form. You don't necessarily have to use that wording, but you can. And so because it's indeterminate form, we're going to go and use L'Hopital's. Okay? So I'm going to rewrite my original limit. The limit as x approaches negative infinity of x squared over e to the negative x. And remember, if we have those indeterminate forms, we can do the derivative of the numerator and the derivative of the denominator. So this is going to be the limit, still as x approaches negative infinity. What's the derivative of x squared? 2x. What's the derivative of e to the negative x? E to the negative x times negative 1. So I'm going to write it as negative e to the negative x, if you will. Because remember, derivative of e to some power is e to some power times the derivative of that power. So derivative of negative x is negative 1. Okay, what happens here? 2 times negative infinity is going to be negative infinity. What about negative e to the negative of negative infinity? There's a lot of negatives in there. So this is going to become e to the positive infinity, right? Which is positive infinity, but then this is the negative of it. So we have negative infinity over negative infinity. So what just happened? We've got an indeterminate form once up here. And twice. We get to use L'Hopital's again. L'Hopital's can be used as many times in a row as necessary till you get to a point where it's not an indeterminate form. So if you're in that 0 over 0 and you keep getting it a couple times, you reuse L'Hopital's. Same thing with infinity over infinities. I think the 2 we did on Friday, we didn't have that. We used L'Hopital's once, then they became solvable. So this one did not. So round 2, so to speak, need to restate my limits. The limit as x approaches negative infinity of 2x is going to be negative infinity. The limit as x approaches negative infinity of negative e to the negative x is also going to be negative infinity. And so again, we can thus apply L'Hopital's. So I'm going to write out the limit I was left at, which was the limit as x approaches negative infinity. Where are we at? 2x over negative e to the negative x. When I take the derivatives, still going to be the limit as x approaches negative infinity. Derivative of 2x is 2. What about derivative of negative e to the negative x? Becomes positive e to the negative x, because derivative of e to the negative x is e to the negative x times the negative 1 for the power, but that negative 1 times the negative 1 that's already out here, so now it becomes just e to the negative x, right?
How do you do the derivative of that?
Okay, so derivative of e to some power is the same, right? So derivative of negative e to the negative x is negative e to the negative x. Then it's going to be times the derivative of my power. So times the derivative of negative x, which is negative 1. And then this negative 1 times that negative will make it positive e to the negative x. You're welcome. Yeah, anytime I try to write stuff out, but sometimes I know oh yeah, sure, we got this, right? I don't always assume correctly, so. Okay, what happens here? On top is a 2, yes? So I know I'm not getting 0 over 0 or infinity over infinity. I know we've come to an end. We're going to have some kind of answer. E to the negative x, so e to the negative infinity is going to be e to the positive infinity, right? Which is essentially the idea of approaching infinity. Now, what do we classify 2 divided by infinity? Keep in mind, we're talking the limit here, right? It's not just 2 divided by a specific number. It's that 2 divided by a number that's getting larger and larger and larger. What? 0. You're getting closer and closer to 0. And this is a limit. Does this mean we're going to hit 0 exactly? Not necessarily. Okay? This is a limit. And so, if you want to think it's 2 divided by an increasingly larger number, if you will, and again, we're thinking, excuse me, limit behavior here, then my answer is going to be 0. Okay? So anytime you have a constant number divided by a number approaching infinity, you're going to say 0. And, proof to yourself. Take 2 and divide by 1,000. Then take 2 and divide by 1,000,000. And, just keep increasing the size of that denominator, and you'll show yourself. Okay? Questions there? Okay, let's try example 4 then. Okay, limit as x approaches negative 2. Now, this would probably be a good one to indicate. Those functions are kind of big, aren't they? Okay, first of all, let's plug in negative 2 and see where we're at before I go any farther. Because here's the deal. Don't ever assume, oh, we're in a L'Hopital lesson, we're going to use L'Hopital's rule. It's an easy thing to do. It's an easy thing to assume because I'm guilty. But always check. Do we really need to use L'Hopital's? So let's see. When I plug in negative 2, okay. already said my numerator was 0. Is my denominator 0 also, I assume? Yeah. Okay. And I'm not saying you have to write that down. That one was just getting bigger for me to keep track of in my head. Okay. So we are in a L'Hopital situation. Now, an option, so we don't have to rewrite those functions a bunch of times when you're doing an open-ended response. We can define those functions to be whatever we want them to be. So we can call them, say, f and g. And then when you write them in your work, you can refer to them as f and g. Does that make sense? So if I go up here, excuse me, and before I ever get started, okay, I define f of x to be x cubed plus x squared minus 8x minus 12. Every time I refer to that equation throughout my work, rather than writing the whole thing out, I can write f of x. My denominator, I'm going to call g of x. So it's x cubed plus 8x squared plus 20x plus 16. This is legal math stuff. This is something that would be accepted on AP. Excuse me. So when I go here to state that both of my limits equal 0, I can say the limit as x approaches negative 2 of f of x equals 0. And I can also, if you really wanted to, you could even say equals the limit as x approaches negative 2 of g of x. That should be okay, right? Because we're still stating separately that they both equal 0. And then I didn't have to write out the 4 terms for each. Okay, so the limit as x approaches negative 2 of f of x over g of x is going to equal the limit as x approaches negative 2. Now, if you wanted to, you could say f prime of x over g of x, g prime of x. However, I really need to see what the derivatives are here, don't I? So, in this case, I would go ahead and find my derivatives. So what's the derivative of f? Three x squared plus 2x minus 8 over the derivative of g, 3x squared plus 16x plus 20. I forgot. I was going to expand this a little bit and kind of squeeze in a by L'Hopital's right there. I kind of forgot that minor detail. So I just kind of put a by L apostrophe H. Okay, what happens when we put negative 2 in this time? On top, I just got 12 minus 4 minus 8. So I got 0 on top, which could just mean we're going to have a 0 answer. However, check that denominator. 12 minus 32 plus 20. So again, we are getting 0 over 0, right? Whether you're doing this in your brain or whether you're calculating. So I'm going to state that both limits equal 0. You can write out what we have right here, or what are these? F prime and G prime. And so that is legitimate. You can say the limit as x approaches negative 2 of f prime of x equals 0. And the limit as x approaches negative 2 of g prime of x equals 0. So you are perfectly fine to call them f prime and g prime because that's what they are. So the limit as x approaches negative 2 f prime of x over g prime of x is going to equal, and this is where I meant to earlier say by L'Hopital, like kind of, you know, it's going to equal the limit as x approaches negative 2 And again, it's going to be f double prime and g double prime, but I'm not going to call them that because I need to physically see them. I guess if you wanted to keep that running list outside here and just say it here, you could. But so what are we going to have? Six x plus 2 over 6x plus 16. Well, my brain says there's no way that can be 0 over 0. I don't know what it is, but my math brain is saying it's not 0 over 0. As hard as this is for me to say, I could leave my answer like this right here.
I don't like it.
I don't like it at all. But officially, you can't leave it with variables in it or anything, but you could leave it right here. Is it negative 10/4? You could leave it like that. This one shouldn't be as bad for you to be able to leave. Or you can go to negative 5/2. Okay? The advantage of leaving it earlier is if you make a mistake in simplifying, you won't get knocked off for, like if you say negative 10/4 is negative 5/4. You've just lost that point because you had made a mistake in your simplifying. So just kind of a reminder that this would be an okay answer. Okay, example 5 when you're ready. Example 5 when I'm ready. Remember which way I ended up doing this. Okay. Sorry, I have a couple different ways I can do this. I'm kind of debating, inner debate here. So, what do you notice if we put 0 in right now?
I'm gonna guess it's denominator 0.
Denominator 0. Numerator, what's sine of 0?
0.
Mm-hmm. Again, I know you guys use the quadrantals, which is fine. My brain goes to sine. This is our basic sine, one phase of sine curve, right? So what's sine of 0? 0. Doesn't even matter what 1 minus cosine x is at that point because we've got 0, right? Now, there are a couple of ways we can do this. And this is where I'm trying to decide which way I want to do this. Previously, we looked at a couple special limits that involve sine x and cosine x. It's been a bit. I don't even remember when it was. Well, it would have had to have been back in our limits chapter. So that would have been unit 1. Okay. So one option here is you can break this up into 2 limits. And the fact that the limit of x approaching 0 of sine x over x times the limit as x approaches 0 of 1 minus cosine x over x. Those limits ring a bell at least? I'm not saying you remember them exactly, but I'm saying do they ring a bell? Because those were 2 we talked about. There are advantages to memorizing them. If you've memorized each of those limits, you can apply those answers right here, and you're done. You don't even have to do L'Hopital's. Okay? So that's an if. Limit as x approaches 0 of sine x over x. Anyone remember that one? 1. Did you find it?
41.
Page 41? Okay. And what are we on? Page 250? So over 200 pages ago. Okay. So one option would be limit as x approaches 0 of sine x over x is 1. What's the limit as x approaches 0 of 1 minus cosine x over x? 0. And 1 times 0 is 0. Okay. I'm going with Maddie's quote of page 40 is where those special limits were. 41. Gosh darn it. I don't know, page 40 gets you in the area. Good enough. Okay. Now, we can leave it at that and move on. Or we can L'Hopital, because here's the deal. What happens in the real situation? Would you catch that?
No.
I'd be honest, I'm not sure I'd catch that. That's me checking against her answer key. I'm like, oh, wait, you can do it that way? Oh, okay, yeah, that makes sense. But you have to, you know, for me, sine x over x is one that I'm more familiar with. I'm not as familiar with the 1 minus cosine x over x. Okay, so you actually, if you wanted to, now, if you look at these individually, sine x over x is 0 over 0, isn't it? And if you look at this one, 1 minus cosine x over x, that's actually 0 over 0 also. Because, and this is where I go with my cosine curve at 0 is 1. Okay, I know, again, you guys use quadrantals, that's fine. It's whatever you use for you. But, so 1 minus 1, that's 0 over 0. One option is we can do L'Hopital's individually here. L'Hopital this piece, L'Hopital this piece. The other option, we go back and do L'Hopital this whole thing. And we can, okay? We can do L'Hopital of this whole thing. And it takes a little bit longer, but in all honesty, it's probably what you would see.
Can I hit the wall? They're slapping the wall right next to me. Oh my god.
Okay, so I'm going to go with. Would you guys would probably just do the whole thing, wouldn't you?
I wouldn't think of breaking it up.
I wouldn't. That's the thing. I don't think you would either. I'm not sure I'd think of breaking it up, so I have to look at it that way. Now, if we do this, how much room do I need here? Okay, so I need to state that my limits each equal 0, right? The limit as x approaches 0 of sine x times 1 minus cosine x equals 0. And the limit as x approaches 0 of x squared equals 0. So the limit as x approaches 0. When we go do the derivative of the numerator, do you want it in this form or do you want it multiplied out? I'll give you a hint. Either way, there's a product rule. And this is what, now, so are you seeing the point that if you caught this earlier, it is easier, isn't it? So I'm going to show you it is doable even if you don't catch it. So I know on mine, what I did is I went ahead and multiplied this out and made it sine x minus sine x cosine x all over x squared. And so then when I apply L'Hopital's, so it's the limit as x approaches 0. Okay, derivative of sine x is cosine x, right? Minus, now we've got a product rule happening. So the derivative of sine x is cosine x times the cosine x that's already there. So I'm going to say minus cosine squared x. And then because this was minusing this term, I'm going to use an automatic minus here because it was a minus sine x cosine x right here. So now it's going to be keep the sign. The derivative of cosine is
Negative sign.
negative sign. So this is going to become plus sine squared x. All over the derivative of x squared, which is 2x. What happens here? Cosine of 0 is 1 minus cosine of 0 squared is 1 plus sine of 0, 0. 2 times 0, 0. What's happening? Here we go again.
0 over 0.
Okay, this is 0 over 0. Now, I don't have enough room. I'm not going to be official here. I'm going to skip the step of stating my limits individually. Don't do that on AP, okay? Obviously, it doesn't matter what you're doing on your multiple choice work. But being official, it wouldn't matter there. So I'm just going to go ahead and jump straight to limit as x approaches 0. I say we go ahead and take the derivatives, if you will. Because again, I don't have the space. I will say by L'Hopital's out here. What's the derivative of cosine? Negative sine minus derivative of cosine squared. It's a power rule first. So 2 times cosine x. The derivative of cosine x is going to be negative sine x. So I'm going to make that a plus 2 cosine x sine x. And then plus the derivative of sine squared x. Multiply that 2 out front, 2 sine x times the derivative of sine x, cosine x. All over, what's the derivative of 2x? 2. Okay, we've hit an endpoint, right? Once you hit the variables, you've hit an endpoint. Do I have a mistake?
No, I actually have a question.
Okay.
So does cosine squared x plus sine squared x equal 1?
You could do,
What?
but
Cosine squared x plus sine squared x.
this is not a positive cosine squared x. This is a negative cosine squared x. I see what you're saying, trying to go with the identity there. And if there's an identity to you switch out, we could. But yeah, it won't quite work there. Okay. Well, my denominator is 2. Sine of 0 is 0. Sine of 0 in the next part is 0. Sine of 0 in the next part is 0. I didn't even do the cosines. Each part has a sign in it, yes? Sine of 0 is 0, so what do we have? 0 over 2, which is 0.
I like the first one a lot better.
If you catch it, right? I get it. I like it too. I have to catch it.
So how does the first guy work?
So the first idea is that back in Unit 1, we talked about these limits as individual limits. And that those are limits that are just good to memorize. Okay, because otherwise, we're doing this extra work here. Because, there's the sine x on top, there's the 1 minus cosine x, x squared can break into x times x. We have all the pieces to break into those two limits. So if you evaluate this first limit here was equal to 1, this second limit here equals 0. 1 times 0 is 0.
I guess I was confused why sine of x over x equals 1.
It's just what
It's one
it
of them.
Wow, that's
It's one of the ones that we looked at the graph at the time. Because the graph does, I don't remember exactly what it does. Is it something like this and then something like that or whatever? It does something. That's not exact. I just remember that it goes up to 1 here. But it's just, and that's why it's one of those that's, because when you go to do this by itself, it's an indeterminate form, right? And so when I put 0 in, I get 0 over 0. Now, you could, when you take these derivatives, you'd end up with cosine over 1. And so then that would work now that we know L'Hopital's. At the time, we didn't know L'Hopital's. So, okay. Is it something like that at all?
Yeah.
Like it?
Yeah.
Okay.
Like
More of a slow curve, not a, I couldn't remember, so.
honestly, when I first looked at it, I was like, it doesn't do that.
It does, yeah. And that's where I said, don't take that exactly. Okay. Example 6. What happens when we put in 1?
I'm gonna guess it's like
I'm going with 0 over 0. Natural log of 1 is 0. That's a good one to know, right? Natural log of 1 is 0. So 0 minus 1 plus 1, gone. E to the first minus e. Well, that's e minus e, which is 0. So, limit as x approaches 1 of natural log x minus x plus 1 equals 0. Limit as x approaches 1 of e to the x minus e is 0. So, I'm getting lazy here. I'm going to say by L'Hopital's and go straight into my limit there. Or getting stressed about time, one of the two. Both. Okay, limit as x approaches 1 here. Derivative of the numerator. Derivative of natural log of x. 1 over x. Minus 1 plus 0. Derivative of the denominator. Derivative of e to the x is e to the x minus derivative of e. 0. Now we plug our 1 in. 1 minus 1 divided by e. Zero divided by e, which is 0.
I saw a 0 on the numerator and I got scared that we're gonna have
Oh, another 0 over 0, and yeah. Huh. And here's the deal. If this was e to the x, if this was e to the x minus e to the x, you would have.
So did we just, like, when we were first doing this, did we just say undefined? We were doing this, or what?
When we were back in the, some of these they just wouldn't give us yet. Because we wouldn't know what to do with them. I mean, it could be that we were looking at graphs at the time, you know, to actually evaluate a limit like this, we wouldn't have it where we were just evaluating because we wouldn't stop at 0, 0 and just stopped. We would have other methods that worked. Because, for instance, looking at a graph will help. Factoring will help at times. You know, there's certain other ways that will help. So, okay, 7. Short or long?
Short.
Short.
Okay.
Factoring.
Huh?
Factoring.
Not factory. Okay. We have to go back to, this even really kind of takes us back to algebra 2 and pre-calc a little bit, but this is a limit as x approaches infinity. This only works because x is approaching infinity. When x approaches infinity, we can look at our powers and think in terms of it like a horizontal asymptote. So if we look at our highest powers, what do you notice about the highest power in the numerator and highest power in the denominator?
Equal.
They're equal. What's the rule when those powers are equal? It's not 1, it's not 0, it's coefficients. Okay? So, this is what you will see sometimes in the homework answer key and stuff, reference of end behavior model. That's what we're talking about there. Okay, end behavior model basically takes us back to horizontal asymptote rules. What are those horizontal asymptote rules? And that's what we can look at here. So we can think of this as an end behavior model, and you can skip L'Hopital's altogether. Now, will L'Hopital's work? Yeah, L'Hopital's would work. I think it takes you twice to get to a point, and when you get to that point, it's going to be, well, it's not going to be 9 over 12 because you will have taken the derivative twice. So it's going to be, I think, 18 over 24, but guess what? It's still going to reduce to be the same thing. So the idea here that the limit as x approaches infinity, if we just look at the 9x squared over the 12x squared, you don't have to know any of the rest of that. It's just the powers match. So you use the coefficients. 9/12, which reduces to 3/4. So if we go back to, basically it started off as rules for horizontal asymptotes in Algebra 2. And we talked about it in pre-calc. But the idea that if it's, you know, how do I want to say? That's not going to work. If powers match, it is the coefficients. And that's what just happened right here. Highest powers match, coefficients. If the larger power is in the denominator, do you guys remember what happens there? Larger power in the denominator. Our horizontal asymptote was y equals 0. And then this doesn't really work here, but if the larger power is in the numerator, at the time we said no horizontal asymptotes. Now, that doesn't really help me in terms of doing the limit, though, does it? Okay, so you'd have to have a different plan there. Now, these are all going to work because we're talking in behavior. This is as x approaches infinity. Or I really should say plus or minus infinity, because it could be approaching positive infinity or negative infinity. Okay. Example 8. Did I give them enough information there? It's kind of connecting back. Limit as x approaches infinity. Okay. If we plug in as we are, you can pretty much tell we're going to get infinity over infinity. Okay. When we get that infinity over infinity, I would have said L'Hopital's here. However, you will notice in the notes some that, you know how we just did end behavior model here, right? What is referred to in the notes is the hierarchy of functions. So right here, why can I not exactly use the end behavior model like we just were? Yeah. We've got x squared there, but when we're using that end behavior model, that's working with polynomials, right? Now, as we look here, e to the 2x is the more dominant, you know, it has more of a rank than natural log of x because it goes up steeper. So you can compare those if you want, and the fact that, you know, which one goes up quicker. Essentially, you know, how do I want to say this? So right here, e to the 2x. If we were to graph these, and you could graph 4x squared and e to the 2x, but if you were to graph these, e to the 2x is going up steeper. Okay? So it is, it's basically equivalent to having a higher power than x squared. And so with that in mind, so you could say that e to the 2x has a greater value than 4x squared. With that in mind, we can go with the idea of bigger power on bottom. What is this limit going to equal if the bigger power is on bottom? It's going to equal 0. You may see that that is done in note sum. Now, what's the other plan? Can we still go L'Hopital's? Yes. Now, should I probably take you guys through L'Hopital's? Or you want to go with this one? Connerson, go with this one?
It saves time.
It does save time, and I am, you know, I will say, I have it here, and I think she has it in, if you look at the notes online. Because when I start going through this one, my final answer I end up with here is 8 over infinity. Like after I go through L'Hopital's twice, what do you know about 8 over infinity? That's a constant number being divided by an increasingly larger number, and so that is 0. But that will take you L'Hopital's twice to get through. Okay? Okay. So hierarchy, e to the 2x essentially has a bigger power than 4x squared, and if you look, it goes up steeper on the graph. Okay? I mean, you have the idea of, obviously that is my variation of 4x squared, right? E to the 2x will do something like that. And so can you see e to the 2x is always going to have higher y values. And so that's how that e to the 2x has a, in the hierarchy of functions, it ranks above 4x squared. It's going to go up quicker. Okay? Okay. I want to talk about a table and hopefully at least a graph, a little bit, a couple of these. You guys got what you want. I'll go on to 9. We have a table. It gives values of a twice differentiable function. Use it to find the limit if it exists. Justify your answer, aka show your work. So, if we look at this as is, I'm going to go ahead and find these limits individually because, you know, the lesson we're in, that's probably going to be that way. If we go to find the limit of the top, realize it's f of 3x plus 2, right? So that means you're putting negative 2 in for x. So this is going to be, the limit of that's going to be equal to f of 3 times negative 2 plus 2, which is going to be f of negative 4. Go to your chart. What is f of negative 4? 0. Shocker there, right? Denominator. Limit as x approaches negative 2 of x squared minus 4 is going to be 4 minus 4, which is 0. Okay, so we know, of course, we need to use L'Hopital's. So the limit as x approaches negative 2 of f of 3x plus 2 over x squared minus 4 by L'Hopital's, okay, is going to be the limit as x approaches negative 2. What's the derivative of f of something? F prime of something. So f prime of 3x plus 2 times the derivative of something. What's the derivative of 3x plus 2? 3. So I'm going to put my times 3 out front. So my numerator is 3 times the derivative f prime of 3x plus 2. Or put it out back. I don't care. Derivative of x squared minus 4, 2x. Okay. Plug some values in and sees what happens. Sees what happens? Geez. 3 times f prime of 3 times negative 2 plus 2 all over 2 times negative 2. And here's the deal. I guess I should have stated this. I went ahead and started working because my denominator is not going to be 0, is it? It's not going to be 0. It's not going to be infinity. I know I'm not using L'Hopital's again. I don't know what's happening with my numerator, but I know I'm going to have something here. So negative 4 for my denominator. Numerator is going to be 3 times f prime of negative 4, if I did my math correctly. So 3 times 8 divided by negative 4. Negative 6. Okay. So there's a chart option, right? Remember, when they give you that f prime, or when you take that derivative and say f prime, don't forget to do the derivative of the inside there. Okay, ready to do a graph? Use the graph of y equals g of x shown below to find the following limit if possible. Use proper notation to justify your findings. Okay, well, let's see. The limit as x approaches 3 of g of x is going to be g of 3, right? When you plug that 3 in to find your limit, it's going to be g of 3. So note, what is this the graph of? This is the graph of g, yes? So g of 3 is 2. Okay. Limit as x approaches 3 of x minus 3 is going to be 0. So what do we end up with here? 2 over 0. What is 2 over 0? So this was the limit as x approaches 3 of g of x over x minus 3. We found to be 2 over 0. What? Don't use the word indeterminate. Undefined. Does not exist. I have D and E written in my notes.
So we're done?
So we're done.
CD is like the easiest thing ever.
We like those answers?
Yes.
Okay. Well. Okay. 11. The differential equation for the curve is given by dy dx. Given that h is twice differentiable and h of 3 equals negative 1, find this fun limit. Okay. Here we go. I'm going to start with top and bottom. So, numerator first, limit as x approaches 3 of h of x plus x minus 2. So, when I plug 3 in, h of 3 plus 3 minus 2. What is h of 3? Negative 1, because it was stated in the given, yes? And we get 0. Okay? Limit as x approaches 3, natural log of 7 minus 2x. It's going to be natural log of 7. I don't know if I really need to say 7 minus 6. It's going to be natural log of 1, which is 0. So what do we need to do? L'Hopital's rule? They gave us a derivative information up above. That's your clue, right? There's your sign. So, the limit. You know what? I'm just going to jump right in. I'm going to say by L'Hopital's off to the side here. Limit as x approaches 3. Derivative of h of x is h prime of x plus derivative of x is 1 minus derivative of 2 is nothing. Derivative of natural log of something.
1 over something.
Okay, so 1 over something times the derivative of something. What's the derivative of 7 minus 2x? Negative 2? Now, this was 1 over the 7 minus 2x. If you can handle it, you can go ahead and put that negative 2 in the numerator in place of the 1. Because that's where it's going to end up, right? Now, we have a mess. Okay, plug in h prime of 3 plus 1. We'll figure out h prime of 3 here in a moment. Negative 2 over 7 minus 2 times 3. Now, could you have rearranged this to get rid of the fraction out of the denominator and that kind of stuff? You can. But if we're also just working with the numbers, you can just keep working. Okay, my denominator turns out to just be negative 2, doesn't it? 7 minus 6, yeah, that's just negative 2. Numerator, what's h prime of 3? We have to evaluate dy dx at x equals 3. So 3 times 3 over y plus 2. What's the y value? Remember the ordered pair, h of 3 equals negative 1. So when x equals 3, y is negative 1, right? So we have 9 over 1, or in other words, 9. So derivative of 3 is 9 plus 1, 10, divided by negative 2 is negative 5. Now, do I have time to explain this last one? Okay, well, what can you, just without doing anything, what you already can tell? 2 infinity over infinity to the 99th, this is going to be an infinity over infinity type situation, right? Now, you wouldn't get anywhere anytime soon with L'Hopital's, because that's x to the 99th.
Yeah.
Okay? You would get somewhere with L'Hopital's, just not anytime soon. So, this is where we would consider which one is growing faster. And I think we'd have to look at the graph to really process this. I mean, technically 2 to the x is growing faster, if I'm not mistaken here. I'm trying to remember, because I have does not exist written down. I'm trying to figure out why.
Sounds good to me.
I'll take that. Dear.
I know. I have to look at it to get more specific here. But L'Hopital's would work eventually, but it would take a while. Okay? I need to relook at that one to be able to explain it better. So I can't remember if anything comes up with it like it in homework that we'd have to be concerned about. We will deal with that tomorrow if we need to. 4.6 due tomorrow. Note I put on the sideboard and it's on Schoology and Skyward. Exam on Thursday is the plan. I will have a plan tomorrow as to what review and all of that. I've worked through the review and the notes. I'm getting ready today to work through another review to decide what I want you guys to do. Okay.